put in your attendances. Okay, so as you can remember, yesterday I stopped at this point and I said this G is the generator for the symmetry or the generator for the coordinate transformation. And if it commutes with the Hamiltonian, or I mean, by commute I mean Poisson commute. In classical mechanics, it means Poisson bracket to be 0, and in quantum mechanics it means the commutator to be 0. So this G is the generator for the transformation. Okay. So from this we found out we found out what should be the condition for this Hamiltonian to be invariant under this coordinate transformation. And we see that in that course we came across this expression, which we wrote as a shorthand like H and G bounded by curly brackets, and we defined it to be the Poisson bracket between this H and G, these two functions of Q and P. So in general, the definition would be if you have any two arbitrary function of Q and P, suppose you have FQP and GQP, okay, then the Poisson bracket between them can be defined to be if G is equal to summation over K del F del QK del G del PK minus del F del PK del G del QK. All right, so just be watchful that in some texts the role of Q and P are interchanged. So in those books the Poisson bracket is defined to be the negative of what I have defined. So physics will not depend on that. I like to keep it this way. So Q first and then P. Okay. Now one easy things to check. So you check different properties already. For example, the linearity and the antisymmetry. So for example, you check properties like this. So Fg is equals minus Gf, things like that, and the linearity and Jacobi identity. And from this definition, you can also check that the Poisson bracket between the coordinate and the momenta themselves, so Qj Pk, okay, this is equals delta Jk, okay, and so this Poisson bracket, this particular Poisson bracket relation between Q and P, we will call this as my fundamental Poisson bracket. Okay, and it will be very important when I talk about transition into quantum mechanics. Okay, so but there is one important thing that follows from this definition. So suppose this I wrote that f is a function of FQP, or in general let us put FQPT also, and later I will talk about only for this function which do not explicitly depend on P. So that gives you this df dt is basically summation over K del F del QK then QK dot plus del F del pk, then pk dot plus del f del t. And again, if you use your Hamilton's equation, then this is del f del qk, and then this qk dot, this becomes del h del pk, and then you again have del f del pk, and this pk dot is again minus del h del qk, right? So plus del f del t. So if you check this, so this is basically the Poisson bracket between f and h plus del f del t. Okay. Now, if f does not depend explicitly on time, then you can drop this term. So for no explicit time dependence, okay, and then you basically have df dt is equals f Poisson bracket with h. So notice that if the Poisson bracket between f and h vanishes, then f is a constant of motion. Okay, so what I have conclusion is, if f h Poisson bracket is equals to 0, then df dt equals to 0, that is f is a constant of motion. And the very watchful of you might notice that this thing resembles very much to the Heisenberg's equation of motion in quantum mechanics. So this is Heisenberg equation of motion in quantum mechanics. Okay, so the classical analog, so the classical version of Heisenberg equation of motion in quantum mechanics. Good. All right. Now you put together two pieces of information. One is this df dt equals f commutator h, and this thing in the beginning, that delta h is equals epsilon h commutator g. Okay. So you notice that if g commutes with h, by commutes I mean the Poisson bracket is 0, then g generates a symmetry. And also, if this commutes with g, then g is also a constant of motion. I mean, that means that g is conserved. So by the Heisenberg equation of motion version, the classical version of Heisenberg equation of motion, if g Poisson commutes with h, then g is a constant of motion. Again, but from this one, I see that if g Poisson commutes with h, then g generates a symmetry of the Hamiltonian. So there is again a connection between symmetry and conserved quantities in classical mechanics, and this is again Noether's theorem in a different language. So this is again Noether's theorem. Noether's theorem restated in a different language. So hopefully you can connect these two. So so the thing that is conserved by virtue of Noether's theorem is basically the generator for the transformation, that is a symmetry of my system, or the symmetry of the Hamiltonian. Okay, so by these two, by combining these two, I get a different perspective into my Noether's theorem. Okay, so I will pause for a brief moment. Yes.
Sir, I have a question regarding this.
Yeah.
We have seen in Noether's theorem that space symmetry produces linear momentum conservation
Yes.
and time symmetry produces energy. Similarly, we can go for others. Sir, in quantum mechanics, in, in coordinate space, IH का del Lx is the momentum operator and IH का del del T is the energy operator. Is this somehow related to Noether's theorem?
Uh, no, actually not. I mean, as I said, the energy and time, that energy and times kind of seems like they behave like conjugate coordinate and moment respectively. That comes from relativistic formulation, because we are in the non-relativistic formulation, we are treating time a bit differently than space. Okay, uh, that connection will be apparent if we look into the relativistic version of relativistic version of quantum mechanics. I mean, the statement you made, I will not say it is correct or wrong. So the way I mean, the thing I mean by that is that if you see the relativistic version of the four momentum and four coordinate, so if you look at your x mu vector, okay, so then this is t x y z, okay, and the p mu vector is the zeroth component is e, and then px, py, pz. So if you go to the relativistic version of quantum mechanics, or relativistic version of this classical mechanics, which would be classical field theory, then you can see that in the same way that my px and x are conjugate to each other, okay, I can, in the same sense, I can talk about t and e. But in the non-relativistic version, uh, the space and time are treated differently. Okay, these space coordinates are function of time. Okay, do I make myself clear? I mean, do you get an idea what I'm trying to say?
Yes, sir. Another question regarding the same. Sir, in XPX commutator in quantum mechanics, we can prove that uncertainty relation.
Yes,
To prove that energy time uncertainty relation, we
there
have
is
to
there is no
encounter
proof
the non-relativistic.
in the non-relativistic version. There is no proof.
Okay.
Okay.
Sir, in different books, they suggest that we can select any other operator and their time derivative to get the delta t.
Hmm, I'm not sure what is meant by that, because there is no operator equivalent to time in non-relativistic quantum mechanics. In non-relativistic quantum mechanics, this x is an operator. You can talk about expectation value of x. There is no operator corresponding to time. You do not talk about expectation value of time. You think that you measure time with definite precision. You are talking about that time. So there is no operator version. So uh, the uncertainty between e and t doesn't come from those operators. It's a relativistic phenomena.
Okay.
Okay, there is no non-relativistic another. In the non-relativistic quantum mechanics, this energy and time, the connection between energy and time are not very apparent. Okay. I can talk about that if I get time when I talk about classical field theory. So that's why we talk about fields, and those fields are basically implicit functions of all of these things, t, x, y, z, and then only we can talk about such things. Let's say. Okay, but the energy time uncertainty is a bit different. It does not follow from operator mechanics. It does not follow from your Schwarz inequality, if you are talking about that. All right. To some degree, I will talk about those things now. Anyway, any other questions?
Sir,
Yeah.
Sir, in translation operator, which you discussed last lecture, u is exponential equal minus iota h t by h code, something like this, sir. And if we'll discuss it in any space, I mean, sir, we are we are talking mm, in momentum space, and we are transforming into and the coordinate is in momentum space, and we are operating it in momentum in the momentum form of translation operator. So does it make sense that the same space would it be, or the space will be different or something else? Because
if you write everything in momentum space, then basically the position operator would be the generator of your momentum space translation. That's it. That's why those two are coordinate.
I mean, sir, we are if we'll try to transform, if we'll try to translate in one space to another, can we? I'm not sure. So
Yeah, you
can
can
we?
do it using Fourier transformation.
Okay, sir. Okay, sir.
That's the standard Fourier transformation.
Sir, generally the translation operator may be in position form and momentum form as well. Because
yes. I mean, what you are considering? You are considering translation in coordinate space or in momentum space. So that basically tells you what is your parameter. What is the epsilon should be identified uh, with the parameter describing the translation. If you are describing translation in the coordinate space, then this epsilon has a dimension of length. So epsilon would be measured in, let's say, centimeter. Okay. If you are considering translation in the momentum space, then epsilon would be measured in the units of momentum. Okay. And then the corresponding generator would be the position coordinate. So G will be identified with Q.
Okay, sir. I mean, generator may be anything. It doesn't mean which space it will from.
Yes. I mean, the which space projection you were talking about. I will discuss those things to some degree right now. Okay.
Okay, sir, this unitary transformation is when the Hamiltonian is constant. I mean, it doesn't depend on time, right, sir? Because when it will depend on time, then integration form will come.
Yes, all the formulation I am describing, I am implicitly assuming, at least for the symmetry related arguments, I am assuming that my coordinate and momentum transformation do not explicitly depend on time.
Okay, sir.
All right. So now, as many of you are curious, what is the connection of with quantum mechanics? So let us talk about that. Okay, so connection with quantum mechanics.
Sir.
Yes.
So just one question, sir. Like, if we take any like arbitrary generator and it commutes with H, so like, how do we go on to find out the particular symmetry? I mean, if it's a like random generator or something, but if it is like commuting with Hamiltonian.
Yeah, you have to find out the small f and g functions, and you get the coordinate transformation.
Okay, so that's the okay.
Yeah.
Sir.
Yes.
Sir, in commutator bracket, we discussed in quantum mechanics that it when it will be zero, and then the observable will be compatible or incompatible when it will be not zero. So, sir, can you talk it in this Poisson bracket as well? I mean, can we talk observable in this point of time?
No, in Poisson bracket, I mean, in classical picture, these are not operators. So, I mean, these are itself observables. There's no expectation value. This x is observable. This p is observable. You do not have to take an expectation value or anything to do that. Okay, so there is no uncertainty relation associated with this, and you will understand why there is no uncertainty relation in classical mechanics, but there is an uncertainty relation in quantum mechanics. That is because how you develop quantum mechanics. Okay, so I'll talk about that. So just wait for let's say 10 minutes. Let me talk for 10 minutes, and then I don't know if I will explain things or I will manage to confuse you more, but let me try anyway. So the first thing, so I do not know how you have been exposed to quantum mechanics so far. Okay, perhaps in your undergraduate days, so you have been talked about some experiments that are not compatible with your classical picture of reality, and then comes Bohr's hypothesis and so on and so forth, and then suddenly someday comes Schrodinger equation, and you accept that, right? Now, so that is one way of doing quantum mechanics. So if you remember correctly, there is no proof for Schrodinger equation, and that is true. I mean, Schrodinger equation can be a starting point of quantum mechanics. You cannot prove that. That's your starting principle, but it's a very good case. Let's say when you elevate these things to operator. There is another alternative picture. I think many of you have been reading in Sakurai's book. So it starts with vector space. Okay, so it starts by assuming that this x and p are operators that lives in that vector space, and they satisfy a certain commutation relation, like x and p is equals 1, x commutator p is equals 1, p commutator p equals 0, and so on and so forth. And basically you can get the whole quantum mechanics from there. And those two pictures are equivalent. So in the Schrodinger picture is usually called wave mechanics, and this one, the abstract vector space formalism, is mostly due to Heisenberg. But I want you to give kind of a like a natural flavor to quantum mechanics, how you can smoothly transition into quantum mechanics from this idea of Poisson bracket and whatever you have learned so far. Okay, so of course I will be using I am not saying that I am any better than the people who did quantum mechanics in 1920s. Okay, so the job for them was very hard because that was a new concept. But now to you, I have the advantage that quantum mechanics is not a new concept to you. So I will be using your already developed intuitions into quantum mechanics to make quantum mechanics kind of more natural. Okay, so the starting point is this. So you see that all these things that I am describing here came from my Lagrangian and Hamiltonian formalism. Okay, so if my Lagrange's equation and Hamilton's equations are there, mostly say Hamilton's equation are there, then I can derive all this. I can come to here. So from so let me start Lagrange. So let me say the Lagrange's equation holds, or let's say variational principle holds. Then I can come here. Yeah. So all the steps I have done in these 13 lectures, you calculate and you arrive here. So Lagrange's equation was your starting point. Good. Now you might wonder, if I start from here indeed, so if I start, let's say this is my Poisson bracket, this is a definition of my Poisson bracket. I do not know what it means. This is my definition of my Poisson bracket. And these kind of things hold. So these things hold. Okay. Then I can basically backtrack all my steps from here to here and from here to here, and then I can go back to my Lagrange's equation. So if this is my starting point, I do not question this part. For example, when I started from Lagrange's equation, my starting point was variational principle or Lagrange's equation itself. I didn't question that thing. Let that be true. And I have a picture of reality, and I found that the things work. And then from step by step, I arrived here. Okay. Now my thing is that I can do a reverse engineering and I can go back to the Lagrange's equation itself. And so it's kind of a reversible process. Now, so it depends. So remember, so from doing the reverse engineering from here to the Lagrange's equation, okay, I have to, so remember, I am assuming this relation, but not only assuming this relation, so this QP equals 1 that I am assuming, and I do not say anything about what is Q and what is P. But to obtain Lagrange's equation, I have to interpret this Q as my kind of position, okay, or the generalized coordinate, or P as my generalized momentum. And suppose these things happen and these things hold, and I get my Lagrange's equation. So see, the interpretation is on my hand. I mean, I develop my own interpretation. The Q and P, if I interpret it as generalized coordinate and generalized momentum, I get my Lagrange's equation. So far, so good. Now I can play an interesting game. Suppose these are my starting point, and I see that the commutators. See, I am not talking about commutators in the sense of quantum mechanics. Suppose I do not know quantum mechanics yet. Okay, I do not know quantum mechanics, but I know linear vector space. Okay, so I know my lessons of vector space. Okay, so I have an idea of vector spaces and operators. Okay, so perhaps you have learned these things in your mathematical methods courses. I'm assuming that. So you notice that the F and G, whose Poisson bracket relations were defined by this, if I do not care about these things, and as I say, so notice again. So I had certain properties of these Poisson brackets. So Fg equals minus Gf, and then say, I don't know, some alpha F G equals alpha F G. So these things you derived, right? And the Jacobi identity, of course. Okay. So F and G are two things, two quantities, which satisfies these things. And then let's say QP equals 1. All these things satisfy things. So one way to satisfy these things is to define Fg is equals, that is the K del F del Qk del G del Pk minus del F del Pk del G. Oh, let me put one variable. So one del F del Q del G del P del F del P and del G del Q. So if I define Fg like this, then I know this happens. But now I start to wonder, is this the only way? So do I have to assume that Fg, this bracket Fg, should always mean this to satisfy these things? Rather, what I am asking is that I need to satisfy these things. These are my fundamental quantities. Then how many types of interpretations can I make for F and G? Okay. So I notice that not only this, but if I interpret F and G as operators, then also these things are satisfied. Okay. So suppose if instead of writing F, G like this, I can write F and G as my operators. Okay, and that this hat means that I am elevating the status of this F and G as operators. And since these properties are shared by the commutator of the operators, so I can call this so the interpretation of this bracket, I call it to be my commutator of f and g. Okay, because commutators also satisfy these properties. Okay. Now you might ask, so if I do this, I will not get classical mechanics back. Of course, I will not get classical mechanics back, because classical mechanics relies not only on these relations, but how you interpret these relations. So the classical mechanical interpretation is that this f and g, this bracket basically means the Poisson bracket, which is defined like this. But now I am trying to devise a new type of mechanics. Fine, I will sacrifice my classical mechanics. I am curious, what type of mechanics do I get if I interpret this bracket to be a commutator? Okay, and I elevate f and g as operators, because operators also share the same properties. The commutator between operators, it share the same properties. I'm just curious. I'm academically curious. Now, but things should not end there. Okay, so if these are operators, so operators do not come alone. I mean, the operators need to act on something. I mean, operators are always defined in a vector space. Without your definition of a vector space, if you do not have a vector space defined, you do not have any operator. So operators always lie in a vector space. Okay, so this f and g, they operate on vectors. Those vectors I label by, let's say, psi. Okay, so these are my collection of vectors that forms the vector space, which for fun I can call, let's say, Hilbert space, or just do not bother about the name. So it operates on a vector space. Okay. Now, so this now you have to assign meaning to these f and g. So these are still abstract. These f, g are operators. They act on a vector space and they satisfy all these things. Okay. Now basically you have to assign meaning to these vectors, to these operators. Now comes the essential part of quantum mechanics. So far it is completely general. Okay. Now you say that these operators reside on a vector space which is given by psi, and so that if you take this inner product psi, let's say f psi, that gives you the expectation value of the observable f. Okay. So now you are, so nobody told you that. Okay, you are now picking it out from the sky. Okay, so this is the Born interpretation of quantum mechanics. Now you are developing, now you are assigning meaning to your vector space. Nobody told you that. You are doing that. Okay, you are saying that this is my, let this be expectation value. Okay, and as soon as you do that, and you say that this psi, this is the total probability, and this should be equals 1, and but the position space and the position space projection of this psi, this is the position space projection of this psi, is called the wave function psi x, and this is the probability density function PDF of finding the system at x. Okay, as soon as you specify these three things, now everything is determined. So these are the basically your Born interpretation of quantum mechanics, and this gives you, then together with this gives you the whole of quantum mechanics. Okay, so you started from this these things, and you try to develop an alternative interpretation of these fundamental Poisson bracket relations. You come with you come to here and you say that my f and g are operators and they operate on these things, and then everything that follows is basically quantum mechanics. But things do not just end there. Okay, you can do further simplification to that. Okay. So what you further notice is that if I have this description of nature, if I say that this is my expectation value, and the expectation value I measure, let's say energy and momentum, these are real quantities in nature. So if this needs to be real, then this f needs to be Hermitian. Okay, so the quantum mechanical operator, if that is a physical operator, this is related to physics, then this f and g, these operators are Hermitian. Okay, usually this f and g are Hermitian. All right, that means f commutator g, let me write, this is anti-Hermitian. Right? So fg minus gf, if you do the dagger, you will find that it is just minus of that thing. So this is anti-Hermitian. So if you write this thing as a, then a dagger will be minus a. Okay. So that's why we extract a factor of I for convenience, so that the remaining part remains Hermitian. So if I write, say, a equals I times a prime, then a dagger would be minus I times a prime dagger. So now if a prime is Hermitian, then I can write is minus I times a prime, then a dagger equals minus a is automatically satisfied. So that's why we talk about that whenever we talk about the commutation relation of two Hermitian operator, we take out a factor of I. Okay, so let's say f g, we take out a factor of, let's say, I. Okay. Usually it is 1 by I, it's the same thing. And in the special case, when this f and g are just x and p, because x and p are the special cases of f and g, and if you elevate the status of this x and p as operators, okay, then if you sandwich these things, these commutator within two states, then what you have is the expectation value of x times p, and the dimension of x times p is angular momentum. Okay, so we take out a fundamental constant that has a dimension of angular momentum, and then whatever remains becomes dimensionless. Okay, so I take out a fundamental constant, say h cross, and so the fundamental constant, which is a dimension of angular momentum. So that's why the quantum mechanical version of this fundamental Poisson bracket relation, I just write, say, q p. When it becomes commutator, I write it as h cross I. This is my starting point. Okay, rather, sorry, I h cross. Okay, so and that's why it makes sense. So I start from this, and then I develop my quantum mechanics, and now you will see that everything will fit into place. Okay, so from this you start your quantum mechanics. Okay, so the mechanics that it develops, because you have interpreted this these relations not using Poisson bracket, but when you interpret these relations using commutator and you assign meaning to those operators and the vector space it operates on, when you assign meaning to them, what you get, not the Lagrange's equation, you get quantum mechanics. To make the connection even further, so those symmetry operations that I have been talking about for so long, the symmetry operations can be understood in a very nice way. So what you have is that perhaps you have in your class of vector spaces, you have been talking about basis transformations. Okay, so basis transformations means you are transforming your basis vectors to a different basis. This is equivalent to a coordinate transformation, like a coordinate rotation. Perhaps Devajyoti have talked about those things. So it usually looks like, so basically, suppose you had a basis vector, set of basis vector E, and you define now E prime, and that is related to say U times E. Okay, so U is usually an unitary metric, so that you can preserve the norm of the basis vectors. Okay, so in the this U is a metric. So in the component form, you would probably write, so E prime J is equals U J K E K sum over K, of course. Okay, so that is the basis transformation. So you go to a different basis. Now, so the basis is our choice, right? So that does not change the physics. I mean, what basis do you do your physics in should not matter at all. So that means if you were looking at some elements of an operator, so suppose there was an operator which I called A. So this A operates on this say so for here it operates on EK and EJ. So that is your jkth element. So this is basically the jkth element of A, if E is your basis vector. So in terms of my old basis vectors, so the A jk was given by this. Okay, or rather basically any expectation values would be given by, so say suppose expectation value of A would be given by say psi A psi. Okay, now you can expand psi in terms of the basis vectors. So if the basis vectors are changing by U, the whole vector would be also changing by the same thing. So suppose psi has become psi prime. So psi prime is basically U times psi. Okay, so I can write it as, what is this? So I can write it as let's say psi. Here I write U dagger U, then I write A, then here I write U. No, I would rather write U dagger here and U dagger U here psi. Okay, so I have done nothing. I have just inserted an unitary matrix into this thing. What? No, this doesn't look right. U psi. Sorry. In both places, I suppose insert U dagger U. Okay. So now you notice this thing. So this U times psi is my new vector psi prime. And this U dagger psi, since it's acting on dual, that is the dual of psi prime. Okay. So this thing basically, in terms of my new basis vectors, this relates to U dagger psi prime. So if you change your basis, so you call these things as A prime. Okay. So in terms of old basis, if the operator was A, so in terms of the new basis, the operator would be A prime, and it would be related to A by this transformation, this similarity transformation. Again, so my new my new operator A prime will be U times A times U dagger. Okay, if my U is my basis transformation. Okay. Now, so in the same spirit, okay, if I now say if A prime is my Hamiltonian that describes my system, so if A prime is my H, then H prime would be given by some U times A times some U times H times U dagger. All right. Now, how do you write a unitary matrix in general? How do you write an unitary matrix? You write it as, like you have now known about group theory. So this U can be written as e to the power I times t, if t is the generator, and times theta. Suppose there is only one generator and there is only one theta. Let us keep things simple. So this is my U. Then of course U dagger is basically, let me call it epsilon. Okay, I will talk about IT epsilon. So in the infinitesimal limit, when epsilon tends to 0, you can expand this thing. So it is e to the power IT epsilon times H, then 1 minus IT epsilon plus order epsilon squared that I do not care about. So in the limit, epsilon tends to 0, right? So the idea here, again, so if you multiply, this is H, then this is ITH, and then minus IHT. So if you do it correctly, then it should be I epsilon T commutator H plus order epsilon square, right? So you notice that H prime minus H, so delta H, which is H prime minus H, is again I epsilon T commutator H. Okay. So it's the, if you note, it's the same relation. It is the same relation as this first one here. Okay. So once you learn that this is the same relation, then you notice that now if my if T is the generator of a symmetry transformation, if T generates a symmetry, then this delta H equals 0, and that means this T commutator H is equals 0, and which according to Heisenberg equation of motion, it means T is a conserved quantity, and so on and so forth. So you see, just by reinterpreting these relations, so these were some arbitrary brackets that I did not know the meaning of. So what I am doing is that I take these to be my starting point, and my physics, what kind of physics I am describing, depends on how I interpret these quantities. So these curly brackets has nothing to do with Poisson brackets here. It's just an arbitrary bracket. It's an arbitrary symbol. So if it happens to be equal to my Poisson bracket, if I interpret this relation as coming from usual Poisson bracket, I get back my classical mechanics. If I interpret these relations as commutators between operators with special meaning to the vector space where it operates on, and so on and so forth, what I get is quantum mechanics. Okay. So I will again pause for a brief moment here and let us see if there are many questions. Is this clear, or you were confused
Sir,
even more?
sir,
Yeah.
sir, here delta H is 0, and can we say that it is because H dash is H, and it will be Hermitian, right, sir? So can we tell this H is commute H is commute here with
No, H prime equals H. That is precisely the condition that your Hamiltonian does not change under the transformation. H prime is not H dagger. H prime is just the Hamiltonian operator in the new basis.
okay, sir.
Okay. Maybe it was a bit heavy for you. I do not know, but you should give it a thought. Okay. Hopefully, you might learn something. You might get a fresh perspective of things.
Sir, can you please slide up?
Okay. Yeah.
Yeah, yes.
Yeah.
So just write down.
Yeah.
Yes, sir. Sir,
Yeah.
sir, why you take commutator of TH is 0 here? Please, can you repeat once more?
It is. I mean, I am saying that if T is a symmetry, if you say that if I change my basis by matrices U, so if I change my basis vectors to the via matrix U, if nothing happens to my Hamiltonian, even after this transformation, if nothing happens to my Hamiltonian, then I will call U to be a symmetry operation. And since U is generated by this T, the condition for U to be a symmetry operation for my Hamiltonian becomes this to be 0.
Okay, sir.
Okay. So this is the idea, basically. I mean, I can give you a trivial problem which you can think about and then tell me the answer. So have you ever thought about, suppose I give you a 2 cross 2 identity matrix. So this is just 1 0 0 1. And I ask you, what are the eigenvalues and the eigenvectors of this matrix? Can anyone tell me?
Sir, 1 is the eigenvalue.
Yeah.
And one eigenvector is 1 0. Sorry.
So E1 is 1 0.
0 1.
What about 1 1?
There is the linear combination of the E1 and E2.
Is it an eigenvector?
Yes, sir.
So how can you be confidently saying that these are the eigenvectors?
Sir, these two spans the whole entire basis and they are orthogonal.
So what?
Sir, if we multiply the matrix by these eigenvectors, then we will get a scalar multiplication of these vectors. Ax is
See, you are not getting the point. If I change the 2 cross 2 matrix, not by identity matrix, this 1 0 0 2, let's say, then the eigenvectors would be 1 0 and it would be 0 1 as you said. But let's say E prime equals 1 1 will no longer be an eigenvector of this thing. Something is special is happening for identity matrix. So I want you to figure it out. Do you understand the question?
Sir, it's orthogonal, I think.
What is orthogonal?
Sir, A transpose, identity transpose remain the same.
Yes. So what does that mean?
So basically, identity matrix is like the combination of the E1 and E2, like the columns and those.
This is also a combination of E1 and E2 with
No,
different
I
vectors.
mean like just its columns are just represented by the eigen.
So
vectors.
what? These columns are also represented by E1 and E2. This is 2 times E2.
Yes.
Sir, while finding eigenvectors like A and B, we just check the ratio for them. Means we can take the common things out from the vector
Okay.
E1.
Okay,
And
do that. The point is, I mean, if you try to find the eigenvectors of identity matrix, you will not be able to find an eigenvector of the identity matrix. Try it and let me know. Okay. It will not give you anything. Have you ever tried that?
Yes. So there x equal to x something like this and y
Yeah.
equal to y.
It doesn't give you anything.
Yes, sir.
So how can you tell about eigenvector of identity matrix?
So by taking a constant, I mean x equal to x, then by taking x something.
I mean, x equals to x is always satisfied. What do you mean? I mean, how can you talk about 1 0 or 1 1? Anyway, think about that. I think the answer is rooted in symmetry. Suppose you call this thing, let's say matrix H1. If this is your Hamiltonian H1 and this is your Hamiltonian H2. Okay. So suppose. So what I am doing by this is that I am doing a coordinate rotation, right? So from 1 0 0 1 to 1 1, I am basically rotating by 45 degrees and so on. And how do I rotate? I rotate by this orthogonal matrix, this cos theta. So this O is equals cos theta sine theta minus sine theta cosine theta, like that. And if you do it in a complex plane, it would be unitary matrix. The thing is, if you rotate these things, so you are now going to a different basis, okay, and then your Hamiltonian should be modified as I said, OH, O dagger, okay, so in the same as this. Okay. So if this is H1, since H1 is an identity matrix, this is O times O dagger, which is equals 1, which is again your H1. Okay. So again, this O is a symmetry of this H1. But you try the same with H2, it will not be equals to H2. So this coordinate rotation is not a symmetry of the second Hamiltonian. Okay. So your ability or inability to find an eigenvector depends on whether there is a symmetry in the Hamiltonian or not. Okay. And you will find the same type of problem when you try to find eigenvectors in the cases when there are degenerate eigenvalues. Okay. So here you see there are degenerate eigenvalues, and so this degeneracy comes from symmetry. The first, so you can look at it from this thing. So if TH is commutator is equals to 0, then means T and H should have the same eigenstates. That means the degenerate eigenstates of H would be, the degeneracy would be labeled by different eigenvalues of T, if you understand what I mean. So whenever there is a, so when there is this commutation to be 0, that means there is a symmetry present in the Hamiltonian. Okay, so this symmetry leads to degeneracy. Here you see the same thing. So symmetry leads to degeneracy and vice versa. Think about these things. Okay, you know the mathematics, but try to figure out the meaning of those things and try to focus on this kind of interpretation. It will help you in your competitive examinations. You will be less confused. So if anyone asks you, give me the eigenvectors of identity matrix, the answer is you can't do that. Any vector would be an eigenvector of identity matrix, but not because of that. Anyways, I think I am, yeah, I crossed my schedule time, so I should stop now. Okay. So okay, and then any quick questions? Otherwise, I will stop. All right, then I stop recording.